You know how to write these things, but as it's going along, write down the little formula, right? Right. You, what's up there, please? Right. So last week we talked about electrostatic forces and so on, right? So today we want to talk about the electric fields and how to find the strength of the electric field. Right? So we know around the electric charge, what is happening? Right. So if I give you a charge, plus charge, right? Around that plus charge, there's an electric field. Okay? So let's say at that point there, we are trying to find the strength of that electric field. Right? In order for us to find the strength of that electric field, what we look at is the force acting per unit charge. That's okay? So the strength of the electric field at that point, F divided by Q. Okay? So the force acting per unit charge at that point is the strength of the electric field. You all remember gravitational field strength? Yeah. How you find that? Yeah. What's the easier version? G is equal to what? F1M. Okay. So whatever. So who's to do it? Right? F1M. Alright, so one thing you will recognize is that every single thing that happens in an electric field, you could compare to what happens in a gravitational field. If I were to throw a mass in a gravitational field, it's follow what part? Projectile, right? So yes, sort of circular, right? Projectile. If I throw electric charge in an electric field, it'll also experience a parabolic path as well. That's okay? Right? So an electric field is defined as any region when an electric charge experience an electric force. The electric field strength, the symbol is capital E. Is defined as the point in an electric field is the force acting. Hold on there. I'm going to show you the whole thing. It's the force exerted per unit positive charge at that point. Quick question. What direction does the electric field move in, Claude? Sean? What direction does the electric field move in? Right? So it goes away from the positive and it goes towards the negative. That's okay. So if I place a positive charge next to a positive charge, how will it move, Shimish? Huh? Away. If I place a positive charge next to a negative charge, it will move towards the negative, right? So, Divish, can I use a positive charge at any point around an electric field to determine its direction? Yeah, yes, right? So in short, we could also use a positive charge to figure out the direction of an electric field. Okay? So the direction of an electric field is the direction in which a positive charge will move. Right? When placed at that point. Right? SI units. SI unit is newtons per coulomb. You all can see where that came from. Force over charge, right? But where did this come from? Move it over this one. Where that come from? See if we can take a minute. See if we can figure out where that unit came from. Take a minute and see if you could come up with that formula. Sorry, with that formula that will give you the unit as PM to the minus. Right now, all we have is Newton per coulomb. But we need something that will help us get volt per meter. All right. Yeah. You all got it? Yeah. You got it? All right. Let us check it out, right? So we have voltage and we have meter. So we know that force is what? Or we can say energy is what? Sorry. Energy is what? Force by distance, right? Correct? So I can take off this and I can write electric field strength as the make F the subject W over T and divide it all by Q. And we know that W is what? Work done or electrical energy is charged by voltage. So that'll be Q by V all over D by Q and it Q will cancel. So electric field strength is beyond T. Give it up? No. But suppose they get something, suppose they get different quantities, you might need it. In fact, I'll show you when one day why you need it. There's a question why you need it. All right, so here's what that's saying, right? That's saying that electric field strength is equal to V on D, right? So if we have a voltage and some separation, we can find electric field strength. So if I give you two parallel plates, one positive and the next plate negative, there is an electric field inside it. And for me to find the electric field inside there, I need the separation D and I need the potential difference B. Okay? So if I have two parallel plates to find the electric field strength, all I need to do is to find the potential difference between the plates and their separation. That's okay? That'll give me the electric field strength. Here's something that's very, very important. Oh, the right down things. E is equal to F1Q, E is equal to V on D, and E is a vector quantity. So it means that the direction when you're quoting is very, very important. Right? The electric field strength is very, very important. And we got some calculations now and I'll show you, right? Just make a note of those things. Yeah, that's the next topic. You want to be able to find the electric field strength, right? It's really big. Right, but that's another option. There's a way that you can put it off, like, can experience, so like take a charge, you want to charge put in there, and that charge will experience. And that was it, you become a little bit more tough. Right? Before we some calculations here, let's just run through this. Scalar quantities, magnitude only, vector quantities, magnitude and direction, right? The electric field lines, right? The electric field lines are represented by field lines. I'm not making no sense. The direction of the electric field at the point is taken as the direction of the force that will be exerted on a positive charge. Right? Remember we talked about that, right? Well, remember this? Right, we talked about this, right? The direction of positive charge will move, right? That's the direction of the force. The field line direction or the tangent to it, if it is curved such the direction strength. Right, oh yeah. So if it's a curve, sorry, if it's a curve at that particular point, you draw tangent and that's the direction. If it's a straight line, well, you know the direction of the field, right? The number of field lines per unit cross-sectional area is proportional to the strength. So if you have plenty field lines, the electric field strength is strong. If you have only a few field lines, then the electric field strength is weak. Huh? Are you okay with that? Now that's some basic info, right? Very similar to magnetism as well. The more field lines they have, the greater the strength. Right here we have some examples of point positive charge, point negative charge, like charges, unlike charges. Okay. Right. We talked about this a little while ago. Between oppositely charged parallel plates, you said that the electric field strength, you recognize how nice and uniform the field lines are. And electric field strength is the potential difference divided by the separation of the plates. Okay. That's what we just talked about, right? Yeah, field potential difference. Right? Next part here. So in a uniform field, the electric field strength constant. Therefore, the force exerted on a given charge Q is also constant. So we know electric field strength is F on Q. So we know that F is equal to E by Q. Right? And since we just found out that electric field strength is V on D, then we can say that F is equal to potential difference by charge all over D. Right? Dipanshu? So here's where the proof would have been important. All right. So before we do anything else, let's try some small calculation. Right? You got it? Oh yeah. Let's try some small calculation. Right. Do me a favor. I want you to find the electric field strength here. Come on. Find the electric field strength in each case. Right, ready? There's some small calculations, right? How to find the strength of the electric field if you have these things. Then we'll talk about direction and thing in the next one, right? Because remember, electric field strengths are what? What type of quantities? Vector quantities, right? Right, so electric field strength is F on Q. The force is 4, the charge is 10. Correct SI units. So that'll be 0.4. This will be Newton per Coulomb, right? Not really realistic, but we're just making up some values, right? Here, electric field strength is what? Is the electric potential divided by distance between them. So that's 4 divided by 0.1. Right? So that's 40. In this case, we can write it as volts per meter. Yeah, in this case, yeah. So we can write it. I'll give it wrong. Right. So let's be a little more specific now, right? So here I have a positive charge, and have a next charge here. That's a positive Q, right? And Q is equal to 4.4 microcoulombs, right? Okay, right. Let's say the electric field strength. The electric field strength here is 2 newtons per coulomb, right? See if we can find the force and the direction of the force exerted on this charge. See if we can find the force exerted on this charge and the direction of that force. There's a positive charge and this is also positive. So what direction will it move in? It will move away, right? That's okay. Like charges repel. That's okay? Nikolai? Like charge repel. So find F from up. Pardon me? Micro is entity minus 6. So good. But the functional stuff. Yeah, but it's okay, let's go. Alright, so F is what? F is equal to electric field strength by electric field strength is 4.4 by 10 to the minus 6. Sorry, I write it wrong. That is charge, right? 4.4 by 10 to the minus 6 and the electric field strength 2. So the force experience there will be 8.8, right? That's okay, right? So I want you to pay attention and remember that all these have directions, right? All right, nice, good. So what will happen here? Are you okay with that? So let's go to a scenario here, Shivish. Right? Let's go to a scenario with a charged particle moving between two parallel plates, right? Right. Let's say I give you a charged particle, it's negatively charged particle, charge Q. Right? And we want to find figure out the force exerted on that particle. Right? We want to figure out the force exerted on the particle travel, and its acceleration. Right? We know that this is negative, so this will be attracted to the positive side. So if it enters traveling like this, because it's attracted here, it will travel something like that, right? Correct? So the particle will follow with something like that. So if I want to find the force on that particle, we know that force is electric field strength by charge. Correct? What is the electric field strength between two parallel plates? E is equal to V over D. So it means that F will be equal to the potential difference by the charge all over the separation. Are you okay with that? Yeah. So if I know the force and I find the mass of this, can I find the acceleration? Since F is equal to ma, A is equal to F1m. So if I put m in here, what will I get? I'll get PQ all over MD. That's okay? So if I put F here and divide it by m, it will look like that. Pardon me? If I divide this by m, where to go? Oh. Right? And then divide it by m, I'll get this. Okay? So that is the acceleration. That is the acceleration of the particle. Right. Right? So I do my favor now, right? So I would like you to find the acceleration that this particle will undergo. If its charge is 2e, right? Charge is 2e. The separation between the plates is 0.1 centimeters, and the voltage is 2.1 volts. I want you to find the acceleration. Huh? Find the acceleration. All right. Let me make it simple. All right. Let's just say the electron. Right? Let's just say the electron. What's the mass of an electron? What? No. Up. So that is the charge of it. 9.11.
Oh, it's neutral.
The mass of an electron. The mass of an electron is 9.11 by 10 to the minus 51. Just give it out of the constant. Huh? No, chemistry, you think we'll charge? The charge is 1.6 by 10 to the minus 90. Well, yeah, next. Are we got you? Right, what you have to do after this, you have to prove the part product. If you come on the board and prove that, Class nine.
Full class done.
No, next week. Right, if you get it. No, yeah, no, second. Time up already. Right, so that's 2.1. Q is 1.6 by 10 to the minus 19. Mass is 9.11 by 10 to the minus 31, right? And distance is what? 0.001. And what you got for the acceleration? Ignore the sign for now. I'll leave it out. Ignore the sign. 3.69 by minus 14. No? Yeah. Oh yeah, let me know that. That's going back. Yeah, well, just give it in physics. Huh? What? Huh? All right. Right. So here's what we're gonna do was Savio. Okay, then. Correct? We have to be able to show this part parabolic, right? Although it's unit 2, it's not going to do the unit 1 stuff. All right. So you need to be able to. Oh, wait, no, ignore that. Huh? Right, online, are you okay there? Aria, are you okay? Are you okay, Aria? Aria, you listening? All right, so we need to go back here and prove this, right? We need to go back here and show the parabolic, right? Right, Nalia, how are you doing this?
So we started with trades.
Oh, you show the parabolic. Right, so first thing is what? What we know about horizontal motion. Horizontal motion, right, is constant, right? Everything will be constant, right? Horizontal motion, the velocity is constant, right? What do we use to prove all these things here? Very good. Very, very good. We use formula. Huh? Equations of motions, right? So v squared is equal to u squared plus 2as. Next one is what? V is equal to u plus t. What else?
Yeah, speed is equal to distance about time.
Right, and speed is equal to distance on time. And we use all these for what? We use all this for vertical motion, right? And we use this one here alone, oh, sorry, online. And we use this one alone for horizontal. So let's let's focus on this part, right? Not the one I would have done in unit 1 like that. We started with as horizontal velocity only. So let's say it moving with horizontal velocity v, small v, yeah? Right? So initial horizontal velocity is v. Right? Divish, well, what is the initial vertical velocity in that case? In this case here, it is 0. That's okay? Yeah? So we know that this vertical velocity staying constant, right? But we know horizontal velocity staying constant. But what about vertical velocity? Does it stay constant? No. Right? So how do we find vertical velocity? 1, 2, or 3? 2. We don't have SS yet. We don't have SS yet, so we can't use these. So we're using V is equal to U plus HT. Right? So we are trying to find vertical velocity. We know initial velocity, we know the acceleration, what we done time, right? So the vertical velocity at any point in time is initial is 0. Gravity going down. So gravity is what? Down, positive, right? So it's positive g by t. So your vertical velocity at any point is g by t. All okay with that? There's unit 1, you gotta learn that. Right? So your vertical velocity is given by this. And your horizontal velocity is staying the same no matter what. That's okay? What do we use? What do we use to show the path parabolic? Which particular equation?
That's equal to U.
Right, we use this, right? So now, let's see if we can figure out the horizontal displacement and the vertical displacement, right? Horizontal displacement, we're using this. Displacement is velocity by time, horizontal, right? Let's call the horizontal displacement x. X is equal to v by t. That's okay? Remember, horizontal velocity staying the same. So the horizontal velocity is v at all times. What about myself?
Yeah.
And now vertical displacement. What's the equation we're using, Ariane? Ariane said S is equal to ut plus a half at squared. S is what? S is the vertical displacement, vertical. So let's use it as y, right? Y is this whole part here. Okay? The vertical velocity initially is 0 by a half gt squared. So y is equal to half gt squared. When I reach here now, there's something I have to do. Very good. You make t the subject come in. So t is equal to x over v. When I put it here, I'll get y is equal to half g by x over v all squared. So I'll get y is equal to half g x squared all over v squared. What does this whole thing show? This whole thing shows that the path is parabolic because y is proportional to x squared. Right? So we're able to show that the path is parabolic. Huh? This is the what's that? That's our next case where you can use sine on tan if it starts off at an angle. This one didn't start on an angle. This one starts moving horizontal. All right. So this you have to be able to prove this. Okay. You have to be able to prove this, right? Nine this morning. Huh? Horizontal motion, velocity constant, and then this. And this is your vertical motion, right? Oh yeah, copy it down. Right, Natalia? Yeah, right? The reason you don't have theta and thing is that the electrons coming into the plate in a horizontal motion. Huh? Yeah, yeah. You can plug in those values to get it here. Okay, so if they ask you to prove it, you have to be able to show all of this, right? They could get values. No, to prove it, you have to use this variation. But we get this back really.
Because that question was 12 months. I could provide.
Forward cross. Yeah, but I never leave it good yet, but yeah. So what, two? I'll be like 5, 6, 7 years. I do want this. Not gonna go. You're done? Vertical displacement is up until here. And here's where I substitute. I substitute 1 to show it parabolic.
Constant, you know.
All okay online there? You're okay, area, this area, you're not listening? Where are you? Show us here. As area, do listen. Area. Where are you? Go on. She was there in action. Anthony again, true?
Yes, sir, normal.
Normal, all right, nice. And do you good?
Yeah, I learn in my work, boy. I learn in my work.
Sick. There, go.
Yeah.
No, I really don't. That's too late.
I don't know, I was looking on the thing, oh yeah, come on. No worry, somebody like should see it out, just. No, no, look at that. How about so? Yeah. Yeah, I think that's the most. I remember, hello, the next game, when I see you, I think.
You really need to work. I don't know.
Alright, ready? All right, Nasser?
So I have that there. So ox, yeah.
Alright, so again, this will come as a proof and they want you to put it together, right? Before we do that. Right, before we do the question on this, there's one thing I want to show you. You all remember how there was something called Newton's law of gravitation? There's something similar here called Coulomb's law. All right. So head up Coulomb's law. Yeah, I'll show you this, and we can calculate it.
Yeah, so we should wait for next week. So, honestly, the class will be as well next week, so we're the following week.
Don't worry, we go protect your heart. All right, so one more thing that we need to catch is this, right? In class, I'm talking. All right, let's say I have two charges, right? Let's say I have two charges and the charges are separated by distance r. Right? You all remember Newton's law of gravitation. You have two, right? You have two masses separated by distance r. There's a force of attraction between them. Well, here, there's also a force between them. It can be attractive or repulsive. And that force is the same thing, proportional to the product of the charges and proportional, well, inversely proportional to the square of their separation, right? So the force between these two is proportional to their product and inversely proportional to their square of their separation, and is given by Q1 on Q2 all over 4 pi epsilon r squared. All right. Which one? This one? This, yeah. No. There's a new one in them. There's Coulomb's law. Right, so of course, the bigger the charges, the bigger is this force. The closer they are, the what? The closer the R will be smaller. So it will be larger, right? So the further away they are, the smaller the force, the closer they are, the bigger the force. right? The epsilon value is 8.85 by 10 to the minus 12. Eight point eight five. Yeah, go give it up. Sometimes if you look at the front of the paper, sometimes you might see that F is equals to, well, not this, but sometimes you might see K, Q1, Q2 on R squared. And this K value, right? That K value is equal to 1 over 4 pi epsilon. So sometimes if you look at the front, there's a value for this. Okay? And sometimes we want you can just use the epsilon value. All right? If you look at the front, if you look at the front of the past paper, sometimes you will see a value for this. Other times you can use the value for epsilon itself. Right? Because this is a constant, right? Pi is a constant, epsilon constant. Right? So sometimes they could just use this value inside it. All right, let's try a small example. I'm sure now you have to finally at least. Finance, please. Keep it showing up there. Right? Finance that please. Find F and then I'll make it slightly complicated, right? I don't build up top of people type question. No, almost done. Now you're finished.
I made feel that.
Not yet? Right, so F is equal to, right, so the force between them will be 2 by 10 to the minus 6 by 5 by 10 to the minus 6 over 4 pi 8.85 by 10 to the minus 12, 0.24 squared. 1.56. No, I did 1.56. The fourth. Online. Are you okay with that? Carry on. Yes, yeah. Everybody okay with that? All right. Okay, so this is basically how you do it, right? Take a look at that scenario there. Right, Nalia? So I'm taking a positive charge, Nalia, and I place the positive charge between two other positive charges. Right? And the separation is 1 meter and 1.5 technically, right? I want to find the force exerted on the positive charge on this Q here. Right? Let me be specific. I want the resultant force, right, exerted on Q. Right? What's again on there? Azaria. So Azaria, look at the Q1. What does Q1 do to the Q charge? All positive, everything positive. What kind of force does Q1 exert on Q? Huh? No, it wouldn't be positive or negative. So it will push it away or towards me. Q1. Away, right? That's okay. So Q1 will push Q away. That's okay. Nalia, what will Q2 do? It will Q2 positive. So what will it do to this charge here? So towards me or in next way? Towards me, right? So, Nikita, how you'll get a resultant force? And Nikita, oh, Ranju. Add them because in the opposite direction.
Yeah, one minus, one plus minus, yeah, that one.
Right? So you find the algebraic sum, one positive, one negative, right? So you'll minus them basically, right? How you know? No matter direction, you could say one positive, one negative. Huh? Yeah, based on your direction, you will know what direction you're going to. Right? So for now, if I ask you to find the resultant force here, you have to consider the force on Q1 and you have to consider the force created by Q2. And you'll get something like this. And then you find the algebraic sum to get a resultant force. How you get F again? Shivish? Shivish, how you getting F? Where are you using? How you getting F here? Huh? We have Shivish. Right, Shivish, we be doing the same thing here, right? Right, we use them. Let me write this here. F is equal to Q1 and Q2 all over. All right? All okay with us? Work it out, man. How I can make this harder, Deepanshu? How I can make this harder? Huh? At a plane, right? So I can do something like this.
Yeah. That's all nice.
Yeah?
I had a.
That's how we do it. We'll do that next week.
Yeah.
Copy down this, finish this one out. Yes. Huh? Can you work out this? No, we almost done. Work out it, please. Hey,
Yeah, kind of a like. Yeah. Nikolai, are you done?
Yes, sir.
One second.
0.5.
Bring it up one second. Oh, yeah, please.
Not done. Hey, here.
Huh?
It's like a variable.
He's a constant. And to give it to you.
What I take my 5 like that. Where are the Elias?
Huh?
Where are the Elias?
Oh, no. This E here is an electron. Charge of an electron. This is charge. Huh? So this is 2 by 1.6. This is 5 by 1.6 by 10. All I got you? Okay, so far?
Yeah.
If you have plus, then you just pay attention to what direction your plus level is. Because based on what you want, right? Come on. How much you got? What level? Online, what you all got here?
Yeah. So we could just minus this.
No, it's different Q values. Right, because Q1 and Q2 is here. Q1 and Q2 is these two. Right? So next we are going to add on electric field strength to this as well. That'll be good. Real quick, and you'll get on. Divided the question. We'll play Friday.
So you can.
After? Yeah. After burn, probably I will. Anybody have lessons on Thursday? What lessons on Thursday? Thursday? What time Thursday? What kind of thing class? I'm going to get. Anthony, where you go, Anthony?
4.22 by 10 to the minus 28.
4.32 by 10 to the minus 20. Anybody get that? 4.32. Right. Good job, Anthony. Got people in here like showing them when work out nothing. All right. So it's important that we understand concept and we'll prove it, we'll put it all together and do past papers next week. Right? So we'll put it all together and build up the past papers and thing next week.
Ask that next week.